Hello all, welcome to the second day of International Space Olympiad training, and let's continue with the telescopes actually. So we have discussed about the basics of optical telescope yesterday, and we have discussed some telescopes as well. And today we will be discussing more on other type of telescope, the telescope that are operating in other kind of lights, something like the X-ray telescope and radio telescope. Mostly we will be discussing today because they both of them are actually different, working in a two different, entirely different way. But other than the infrared is actually almost the same like that of a optical telescope. Some difference are there based on the material selection and all. Other than that, it is almost the same. But X-ray telescope basically it is entirely different, and radio telescope also. Okay, so that will be discussed mostly, and also about some famous, the most famous maybe telescopes in space will also be discussed here. Okay, so before going to that, let me start with this slide that actually gives you the importance of why we need a space telescope, or why we have to send telescope to space. Okay, so let's see. So assume that this is a diagram. In this diagram we are actually showing, so here this is the opacity basically, so how much opaque the atmosphere is. So imagine here this is full. Okay, so here this is full, here there is a dip, and here again it is wiggling something like this, and again it's maximum, then dipping, then maximum. So the meaning of that, this means it is completely opaque, or it blocks that certain kind of light completely. So here what comes, so this is a visible light, and the visible light here you can see a gap. That means almost all the visible light is reaching the Earth's surface, or atmosphere is almost transparent to visible light, but it is not completely transparent. It blocks some amount. You can see a tiny amount is being blocked, but anyway it can reach the surface. But here you see that this is the radio window, and almost the main radio waves are actually reaching the Earth's surface. And here you can see some part of the infrared also reaches, and here also some more infrared, but many of the infrared is actually being blocked here. And especially more importantly, you can see gamma ray, X-ray and ultraviolet. Especially gamma and X-ray is completely being blocked here by the atmosphere. It's actually good. That is why we evolved like this, because this high energy gamma ray and X-ray and even ultraviolet is not that good for life to evolve in our Earth, or maybe or this way. Maybe if gamma ray and X-ray were reaching here, maybe some other kind of life may have evolved. We don't know. Anyway, this is actually a boon for us, but at the same time, for astronomers, we cannot actually place a gamma ray telescope or X-ray telescope on surface of Earth. Even if we make something like that, we cannot actually put it on the surface of Earth. We have to send it above our atmosphere, either by using a balloon or by using some rockets, or even as a satellite. Okay, so the telescopes that are sent as satellites to orbit around Earth, and so that they can okay, so that they can observe all this wavelength without the obstruction of atmosphere. And those telescopes that are orbiting maybe around Earth, maybe sometimes some other location, anyway they are all in outer space, and those telescopes are called space telescopes basically. So the one of a kind, or the one of the main type of telescope which we cannot place on Earth's surface is X-ray telescopes, X-ray and gamma ray. Both almost works on same kind of principle. Anyway, we will discuss about X-ray here. So X-ray telescopes. Okay, so an X-ray telescope, usually known as XRT, okay, is a telescope that is designed to observe remote objects in the X-ray spectrum. So X-ray, as we mentioned yesterday, they are all high energy rays. Okay, so any high energy event that are happening, even the sun's fusion, the energy fusion is happening inside the sun, that even emits X-ray. And supernova explosion, maybe gamma ray burst, or maybe active galactic nucleus or quasars. These are all source of X-rays actually. So all the high energy events are actually emitting X-rays. So X-rays are everywhere in the around in and around us. Okay, around us in the sense that in space actually. But anyway, luckily it is not coming to Earth's surface. So almost our X-rays are actually absorbed by Earth atmosphere. So instrument to detect X-rays must be taken to high altitude by balloons or sounding rockets or satellites. So basically, sounding rockets or satellites can be used for observing X-rays, but for a short period only, because we cannot keep it there. Okay, so to keep it there, it has to orbit around something, or it should be a satellite. So this telescope, what you're seeing here, this is Chandra X-ray Observatory, which is also a satellite. And for X-rays, an interesting thing is that we cannot use usual mirror or lens. What we have seen for optical telescopes cannot be used here to focus X-ray. So to focus X-ray, if we use a mirror or some kind of a lens or usual things, the problem is that either that X-ray get absorbed by that lens, or maybe even it pass without any deflection at all, okay, or without any reflection or any change in its paths. So if it's a mirror, imagine the X-ray is coming, X-ray will pass through that. Either it will be absorbed by that, but anyway it won't reflect back. Okay, so that is a problem with X-ray. Even with any material, if you try, the main problem is that if you make any material to make a usual mirror, a parabolic mirror, X-ray will come and it will pass or absorb. It won't get reflected back to a focus point. So that actually they came with a clever idea, or there is another interesting idea, that they take some kind of a polished metal, okay, and suppose this is the X-ray coming, and in the path of the X-ray they place it not exactly perpendicular or at a higher angle, they place it at a grazing angle, okay, a tiny angle. So the example is here, you see, this is here, so it is coming here, and since it is a very tiny angle, it get deflected or reflected here. Okay, if you make that angle more steep, then it get either absorbed or transmitted. So here, since it is a tiny angle or a grazing incidence, it can actually pass through here. Here there will be one. So when it pass through one, it can deflect and go like this. And we place one more here so that it once again deflect and it can finally reach the point. Okay, so place something similar to that concentrically, something like a ring like structure, a number of them, then it can actually focus all the light that X-rays are coming to that point. Nice. So that is the way how X-rays are being focused using a grazing incident mirrors. So those mirrors are known as grazing incident mirrors. So this is the real picture of that. So what you are seeing here, you can see this is an X-ray imaging spectroscopy mission by JAXA. So from that JAXA mission, this is what you are seeing. Okay, here if you zoom in, you can see that this something like tiny gaps are there. So through this gap, so that an enlarged diagram of that is being drawn here. So this is, we can call it as an X-ray lens or an X-ray mirror, which is able to focus X-ray to a point. So that is one method of getting X-ray to a point. Another method is something called collimated apertures. So collimated apertures means it will be something like a tiny hole, so that there will be X-ray coming in all this direction, but only what is coming straight will be passed through small holes and finally reach a point. And to get the image of that source, what they do is that they put something like this mask. Okay, this is called a corded mask. You can simply imagine it like, take an opaque thing and put some holes, some random, a pattern. Okay, a pattern will be put here. Okay, it is not an image. Okay, a pattern. And now imagine that if I shine a torch from this direction, it will make a shadow in the behind screen. A shadow of this will be there. Okay, and similarly, if I send another light from here, it will also make a shadow. But the shadow's property, how big it is, how slanted it is, whether it is elliptical or what are the changes, how intense it is, all these things depends on the source of light, whether it is coming from a long distance away or whether it is closer, or it is in what direction it is coming, how bright it is. Depending on the light source, the shadow will be different. So by analyzing the shadow, by knowing this pattern, actually we can figure out what the source is. So this is the same thing happening here. So assume that you have an X-ray source from here and here. Both are actually making two different types of shadows. This is one shadow, This is one shadow. Actually, from this shadow, we can actually reconstruct the original image. So that is another method that is used for X-ray telescope. So it is called a collimated apertures or corded mask apertures or corded mask. Okay, so that is two methods, but mostly for telescope it is used a grazing incidence mirror. Okay, so here also in the Chandra X-ray telescope you can see the front. Okay, it is not usual. Okay, this same thing. If you look closely, you can identify that it is actually something similar to this is sitting there as well. So this is the X-ray mirrors, and using which we can focus the light so that we get the images. So this is one of the most famous X-ray observatory, that is the Chandra X-ray Observatory, and it is previously known as the Advanced X-ray Astrophysics Facility, but later it named after Subramaniam Chandrasekhar, a Nobel Prize winning Indian American astrophysicist, and I hope you know his name by Chandrasekhar Limit and all. So it's launched in 1919 by a space shuttle called Columbia, and the mission was STS-93 by NASA, and it is actually sensitive to X-ray sources 100 times fainter than any previous X-ray telescope at that time. Okay, so and it is an Earth orbiting satellite, and which is just a second. Okay, in a 64-hour orbit, and its mission is ongoing as of 2025. So the mission is still running, and it's almost 24 years already. Okay, and the diameter of the mirror is 1.2 meter. And one more important thing regarding this, there are some certain telescopes are together called great observatories by NASA. Okay, so those great observatories are, one is Chandra X-ray telescope, the other is Hubble Space Telescope, and this another one is Compton Gamma Ray Observatory, and the other one is Spitzer Telescope. Okay, Compton Gamma Ray Observatory is, so actually if you look at this, all these are working at different wavelengths. So Chandra X-ray Observatory in X-ray, then Hubble Space Telescope mainly in visible and UV. Okay, and some infrared as well. Okay, but infrared is not that much, but anyway, visible and UV, some infrared. Then Compton Gamma Ray Observatory is in gamma ray, and Spitzer Space Telescopes in infrared. Okay, see, so that is how it is working. Okay, anyway, Spitzer, Compton and Spitzer are not working right now. That is, yeah, it is decommissioned. I think it ran till 2000, and this is till 2020 actually. So this is about the Chandra X-ray Observatory. Okay, then the next one is X-ray Multi-Mirror Mission Newton, XMMN. Just a second. Okay, that is another by ESA, European Space Agency. This is also still running almost as the age of Chandra X-ray Observatory, and it is a multi-mirror telescope in the sense that you can see here it has one, two, three X-ray telescopes are there, but each of them has they are not that big. They are 70 centimeters the outer ring mirror diameter, you can see, and that is three of them are there. That is why it is called a multi-mirror mission. Okay. The next thing about this is along with the X-ray, it has an optical telescope as well, which can observe in visible and ultraviolet wavelength. Okay, it also associate along with this. There is a small optical telescope as well, but it is not as important that of the X-ray telescope. But anyway, the advantage is that at the same time they can actually take the picture in X-ray, and the same location can be imaged using the optical or the visible and ultraviolet. It is actually an additional benefit actually. And ESA is planning to succeed XMM Newton with another telescope called Advanced Telescope for High Energy Astrophysics, or in short it is called Athena, to be launched in 2035. And the specialty of this is, again, it's an X-ray telescope, And X-ray and gamma ray are the high energy wavelength energy light, and the study of astronomy using those lights are come under the field of astrophysics called a high energy astrophysics. Okay, so that is why it is called a high energy. Okay, because they are dealing with the high energy wavelength or high energy lights. Okay, then okay, then let's go and discuss about the radio telescope. So the radio telescopes are again they are all ground-based telescopes. Advantage is that the radio can be received here. Otherwise, just imagine that there is a yesterday we actually discussed an equation called theta is equal to 1.22 lambda by d. Okay, so in this we mentioned that theta should be smaller for a powerful telescope to have things separated, or for a high resolving power theta should be small. And for that, one thing we can do is we can increase the d. But what about lambda? Okay, so when it comes to lambda, you know that if you make a telescope in radio wavelength, already this lambda is too big, something of the order of meters. Okay, so since lambda is of the order of meters, then the diameter should be so large, then only it can get some good image. So for the resolving power to be higher for a higher wavelength, or because the wavelength is in the numerator, then the only thing we cannot actually control the radio wavelength. Okay, so it's fixed, we cannot actually make the radio wavelength to change or anything. The only way we can do is that radio wavelength anyway it's fixed. The only thing we can make is the diameter to be larger. So to make the diameter larger, it should be so large when compared with an optical telescope of it is so big. Okay, that is the speciality of this. But anyway, one advantage is that the surface of the telescope is not need to be polished well, something like a mirror. Okay, even you can see when you look through this telescope, it is almost transparent. Okay, but you can see that here, if you look closely, it is something like a mesh. It's a wire mesh. Okay, it's so close by wire mesh, and this wire mesh even can actually deflect the radio waves. So for deflecting the radio waves, there is no need for having a mirror. Okay, you need big things which is shaped like this can actually reflect wavelength, longer wavelength like the radio waves. So the radio waves will be reflected. This is something similar setup that of a mirror telescope that we discussed last day. Something like there is a concave mirror. So instead of that concave mirror, we have a dish. Okay, and this dish now the radio waves are coming. It will hit the telescope dish, and it will be reflected to the center or the focus. Okay, so another wave will come in this direction. It will get reflected to this point, and another will come. Okay, and it will also reflect it to this point, and at this point we will place something called a receiver. Okay, usually for a telescope there can be a secondary mirror or a camera. Here instead of that we have a receiver. That receiver unit will actually record the signal or receive the signal, and it will be sent to the control unit. Okay, usually near to that, and that is how it is working. So it is so simple like that, but the mirror is a bit different. We won't call it as a mirror. Anyway, it is actually a mirror for radio wavelength, but we won't call it as a mirror. We call it as a dish. Okay, that dish can actually focus the radio waves to a point where it is being recorded. Okay. Okay, an array of smaller dishes. Okay. Now, the collected waves are focused into a receiver. Okay, and okay. So then that is analyzed for whatever it is there and for scientific purposes. So that is basically the radio telescope, how it works. And majorly there are two types of radio telescope arrangements are there. One is called a single dish telescope. So they will be a single big dish. Okay, that will be there. The best example is Arecibo Observatory, or there is one in China that is a 500-meter big one. So these are all single dish. Okay, there is only a very big dish, that is the single telescope. And there is another thing that is actually instead of making a big dish, they will make small telescope, small radio telescope like this. See, like this. and they will be arranged in a specific pattern so that they get a single telescope. The effect of a single telescope can be synthesized here. Okay, so I will explain about that in the next slide. It is called the radio interferometry. Okay, so in radio interferometry, the idea is that either I can make a telescope, a big one. Assume that this is 1 kilometer in radius, that means 2 kilometer in diameter. So instead of making a big 2 kilometer diameter telescope, I can take I can make, so it is a big one. So just imagine that usually I will show you a half-kilometer telescope in the next slide. But anyway, that half-kilometer telescope is not steerable in the sense that I cannot orient it to whatever direction it is needed. Uh, but small, if the telescope is smaller, I can actually tilt or steer it to whatever direction it is, to an intended direction. But here it is not, we are not able to move it like that. So what we do is that instead of making a big one in the same area, so this is, you know, that this radius is 1 kilometer. So I will make a line something like this in a almost a Y shape. Okay, so the one arm is 1 kilometer, this is 1 kilometer, this is 1 kilometer. Now this is just a line for a reference, and I can place telescopes here: 1, 2, 3, 4, maybe 5, 6, 7, 8, 9, 10, 11, 12. Okay, something like this. Maybe more than that. The number depends. Anyway, this much number of telescopes I am making and fixing it here. So what happened here? So I'm not making a big telescope like this. Instead of that, at the same place, I will be placing smaller telescope together. And now using a technique called very long baseline interferometry, or VLBI, I will explain a bit about that later anyway, but using the technology, I can actually make this telescope as big as this. Okay, so effectively this telescope will act like a single dish of this size. So what is the advantage? I can actually make small dishes instead of making a big one, and I can actually move them independently. And now if I have an object here, all this telescope will be, or this individual telescope will be pointing towards that object. Okay, so here also you can see that all of them are actually aligned in the same direction to observe something. And one more interesting feature about this radio telescope is that it even works in the daytime. Okay, there is no need for to wait for night actually to work the radio telescope. It works throughout the day when compared with the other optical telescope on ground. Actually, it can even work in the nighttime as well, night and day as well. Okay, so here that is this technique of making is an arrangement or an array of telescope, radio telescope, into a big aperture, which is called the very long baseline interferometer. And to work this, actually, they are usually using a technique called VLBI. And in this, they collect signals from all this telescope. Okay, so now just suppose that an object is here. Okay, an object is here, and the signal is coming from this object, and you know that it is actually emitting radio in all direction. Maybe it is so far away, so it is coming something like this. But anyway, when it is coming, you know that uh, you know that this telescope will receive that light first, light in the sense that radio wave first, and this will get it bit later, and this will get it again later, and this will be the one to receive it at last. Okay, he will be the one, or he or she, this telescope will be the one to receive it at last it will receive. Okay, so it will get first and it will get last. Now when it receive, along with that, it will be time coded. Along with that, precise time using atomic clocks will be recorded along with that. So at what time we received this, and at what time this received. So we do have the signal as well as the exact time at which it received. Okay, now based on that time difference, we know that how much gap in there is in between. Even though that gap is so tiny, and the radio waves are also traveling at the speed of light, but there is a time lag between this telescope and this telescope. So this received the signal first, and the last one received at last. Okay, so that means, okay, there is a time lag. So So we know that what is a time lag. So by knowing that time lag and the coded time, we can actually add all those light together so that it is equivalent to that of a big telescope. So that is called the very long baseline interferometry. And we might be imagining that this will only work for a small area like this. But if you remember in 2018 or something, uh, we imaged a black hole, basically the accretion disk of a black hole. If you remember that donut like looking image, then that is actually captured by this method of interferometry, radio interferometry. And those telescopes were not something like this 21 kilometer or anything. It was actually placed, the telescopes were from different part of Earth. So assume that this is Earth. There are telescope here, 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 and many telescope. I don't remember the number of telescopes actually. Anyway, a number of telescope from different part of the Earth came online at the same time, and it pointed towards that what is called the black hole, and it imaged it. Okay, and effectively all this telescope, when it comes together, it is almost equivalent to that of an entire telescope. So when I am saying that it is equivalent to that of an entire telescope, okay, it is not about the brightness of the object. Okay, anyway, that brightness is less when it is small. So you might be thinking that then it is always better to make this kind of telescope always, but I am talking about the resolving power. Okay, so the resolving power will be better when you make small telescope, but anyway the brightness won't increase much. Okay, that means, so if you have a telescope, a single dish telescope like this, and effectively assume that I have a another array of telescope like this, both have same diameter, but now both of this will have the same resolving power, but the brighter signal will be in this. Okay, so better signal will be in this single dish, because we are actually losing signal from all this other area where the telescope is not present. So anyway, it is not equivalent in the sense that they are always the same. Okay, but it is equivalent in the sense that they both have same resolving power. Okay, and for imaging that black hole imaging, what we need is other much better important is the resolving power. So everything, many telescope on the one side of the Earth came online at the same time, and they recorded those data along with the precise timing and all. And actually they carried this data in huge hard disk actually by flight, and it took to the same place, and they analyzed it so that they were able to generate the image that we you might have been seen in internet and all, that is imaged in 2018. Okay, so that is about the very long baseline interferometry. Okay, so that is another kind of thing. And this project of imaging the black hole, if you remember, that is called the that entire called the Event Horizon Telescope, EHT. That is the just a second. Okay, so that is called the Event Horizon Telescopes, which image the that black hole. Okay. Now this is another single aperture example. I think this is the largest one, nicknamed Tianyan. This is a Chinese one, and the size of this is actually 500 meters. So from one end to one end, this is half a kilometer actually, half kilometer this is, and this is that huge single aperture dish. And you can see here, we cannot actually make a dish like what you are seeing here. Okay, something like this. Why? Because if you cannot make such a big construction and make it steerable, so instead of that, what they are doing is they are fixing it a basin, something like a natural dish that occurred between the mountains. Okay, and you can see that basin is here, and they constructed one, and whatever is above the earth or whatever comes above it can be observed. Anyway, it is not tiltable or steerable. Okay, it is something like that for a liquid mirror telescope, which cannot be steered to any direction. So it is also always looking at the exact midpoint of the sky. Okay, so that is about the 500-meter aperture. The next one is the Arecibo telescope. It is actually collapsed due to some instrument. It's actually decommissioned in decommissioned and in 2020, and it's actually collapsed as of now. And yeah, in December 2020, it is collapsed, and some instrument got failed, and that is why it is decommissioned. And actually, it collapsed because of some hurricane or something happened, something like that, some natural not a calamity anyway. So it's a hurricane actually that is actually caused the collapse of this telescope, and its size is actually comparable with the what we have seen in the previous slide. That is actually it is 305-meter of size, and it is actually featured in some movies, something like in one James Bond movie. It is there, some action scene is actually happening inside this dish, and somewhere here hanging here and something like that. So that is it. So here this part is acting as the dish, and this dish can actually reflect, and this is the receiver unit. It can actually, this receiver is actually suspended by 3 wires from this side. Okay, now this is another array of telescope called a very large array telescope, or short we call it as VLA, or the full name is actually the Karl Jansky Very Large Array. So Karl G. Jansky is known as the father of radio astronomy. Father of radio astronomy. Okay, so it is named after him, and usually, but most popularly, it is known as Very Large Array or VLA. Okay, so it is actually 25-meter. A single dish is actually 25-meter, but there are 28 of them are there. Okay, so 25-meter is the size of one dish, and there are 28 of them are arranged in a Y shape. Okay, and it actually span a size of some 21 kilometers. See, this is only 3 and 3 are there, so it is only 9. You can see a part here, this is only 10. Now there are some 18 of them are actually there, and they all together get a shape of Y, and it is together act as a single telescope, equivalent to that of a single telescope, and that is called the VLA or Very Large Array telescopes. Now let us discuss about some space telescope. Popular one, and the most popular one is the Hubble Space Telescope. And the Hubble Space Telescope is the most famous telescope, maybe. Even if you consider the Earth-based telescope or anything, the Hubble is so famous. So it is so famous because it is running from 1990. Okay, now it is actually 25 plus 10, almost 30, 35 years actually. So that is one thing about it. So during this long run, it is actually able to even revolutionize astronomy actually. It is able to determine the age of the universe uh, accurately, and many images. So many images that is actually, you can see this one, the pillars of creation, and many of them even we use in many other, maybe even as the wallpaper. So got a lot of public attention as well. And one advantage of this telescope is that it is a serviceable telescope. Serviceable in the sense you can go and take the telescope and repair it. So you can actually go in space shuttle or maybe in some rocket, and you can actually move along with the telescope, okay, in that orbit, and you can get grab that telescope and get back, and you can actually service it. So you can upgrade something like what we use for do for a PC or a car. Okay, we can actually upgrade the thing, something like you can upgrade the RAM or maybe the camera. So here also camera and things can be actually upgraded. So upgrade is possible, or servicing is possible for this telescope. It made in such a way. Okay, so it was actually lucky we made it in such a way. Otherwise, once it is launched, there is a problem actually. So its launch date is April 24, 1990, and some okay. Then there is a service happened in May 20 itself. I will explain about that. And the mirror diameter is some 2.4 meter diameter, and focal length is 57.6. Then its design is a Ritchie criterion reflector, and collecting area is something like 4 meter square. Okay, and it can observe in near infrared. So what is near infrared? Okay, so there is near infrared and far infrared. So before that, yeah, it can also observe in visible and ultraviolet. Okay, so if you take that, if you remember that electromagnetic spectrum, so here it is visible light, it is a tiny window, visible light. Okay, then here we have some ultraviolet, here we have some x-ray, and here we have some gamma ray. So this is the letter for gamma, if you know. Okay, or simply gamma ray. Okay, and here it comes the infrared, and then microwave and radio waves. Okay, now this is our visible light. Okay, and this is violet, indigo, blue, green, or okay, yellow, orange, red. Okay, so then infrared, that is near to visible, that means some this part or this part is called the near infrared. So infrared that is far away, that is called the far infrared, and there is a mid IR that is in between. Okay, so it can only observe the near infrared and visible light and ultraviolet. Okay, so these are also beautiful. This is actually two interacting galaxies. So it is something kind two galaxies are actually kind of merging together. So that is what you're seeing here in this picture. So this is also from Hubble. But even though it revolutionized astronomy, just after the launch, the first images were actually blurry. So when you take pictures of stars, especially faraway stars, even with any higher telescopes, those stars will look like something like this. You can see here. Okay. So we cannot actually image any other star, something like a sphere, like our sun, because the stars are so far away and they are so small. Okay, so it will appear as a point object. So we call stars as the point object in astronomy or in telescopes. Okay, here you can see this is a point. But once the telescope is launched to space, and when we got the first images, these points should be sharp like this, but all these points got blurry. Okay, so something like here you can see this image. Okay, I think this is the Whirlpool galaxy, if I remember correctly. I don't know. Anyway, this is a galaxy, a spiral galaxy, you can see. So the first image is something like this. Okay, so something happened here is something, the polishing of the mirror wasn't fine. Okay, so just imagine that it is a space telescope, not a ground based one, and they said that, and this is one of the most finely polished mirror ever, maybe. Okay, so the primary mirror had been polished to the wrong shape, although it was believed to be one of the most precisely figured optical mirrors ever made, smooth to about 10 nanometer. It's even in nanometer level it was smooth, but something happened, some wrong polishing has happened, so that the images were actually useless, kind of this. Okay, so then what we can do, so either we have to decommission or we have to left that mission, otherwise we can do some correction. And in 1993, first service mission actually happened. So during that service mission, what they did is something similar to that, an optical corrector. So we know that when there is some issue with our eye, we use a specs actually. So something like a spectacles. Okay, so which is actually correcting for the eyes, that spherical shape or something. It is actually nothing happened to the lens actually for our eye. It is happening for the eyeball. Maybe it elongate or contracts. So based on that, we put something like a glass in front of us. Similarly, they actually corrected it using by placing a corrective optics. Okay, so there is a problem with this polishing. So to counteract that, they actually figured out a corrective optics. And just imagine that the service, it's launched in 1990 and it is only corrected after 3 years, almost 3 or 2 years they were able to correct, because they have to, there is no way to access that telescope. Just imagine that we are in ground,
Okay, and just by analyzing these pictures or photographs, they have to figure out what exactly happened to the mirror, or at which place actually that error is happened, and based on that they have to make a correcting optics. Here they cannot actually test it, something like when you go to a eye specialist, they actually try one glass. Is it good? Okay, this is not that good, then check with another one, or this is better, or this is better. We do that actually. So that kind of a testing is not possible there. But anyway, luckily there is an identical mirror like this already made. If something happened, they need a copy. So they had an identical mirror. But the problem that we cannot take that identical mirror to space. Okay, because it's huge mirror and we cannot replace it there in space and all. So it is impossible. So by using that mirror at ground, they were actually able to test in even though it is not directly testing the telescope, they were able to test and all. Then they could make a corrective optics, and it is usually called COSTAR. That is the corrective optics. The expansion is something like corrective optics space telescope axial replacement, and they replace, that is this thing that you are seeing. Okay, this is that instrument, and they in an Endeavor, about Endeavor is a space shuttle. In that Endeavor space shuttle, they went and repaired it, and then they got a better picture. And it is something like, it got not better, the best picture. Okay, we cannot call it as a better picture. They corrected it and they got the best pictures, and that best picture you can see that before and after. So people who are having a specs, you know that when you wear it and with and without that specs, you, when you read something, you know the difference in clarity. So the similar clarity difference happened here as well. Okay, so that is about the Hubble Space Telescope service mission. Okay, and there were multiple service mission. I don't remember the number of multiple missions that happened, but anyway, final mission happened in some 2000s actually. And there is a famous IMAX documentary uh, that is actually filming all the processes behind the last service mission, their training, and even the space visuals are also shot in IMAX actually. And I couldn't see it in theaters anyway, but anyway, that is available actually in internet. You just Google for IMAX Hubble. Okay, so you can get some very high quality images, high quality documentary. So it explains all these things there. So that is about the Hubble. And these are some major things, major important discoveries regarding Hubble Space Telescope. Age and expansion of the universe. So the estimated age of universe is actually something between 10 to 20 billion when before Hubble Space Telescope, and that later we were able to fix it to some 13.7 using this. And the existence of black hole were confirmed, not directly imaging it by using other methods. They were able to uh, make sure that the black hole exists. And there are another one in March 2019, using the help of Gaia. Gaia is another space telescope which is actually measuring something called a parallax. Okay. So it is actually observing it, all the stars, and measuring it parallax. And using that parallax is a method of measuring distance. Okay. So by getting the parallax, the Gaia can actually measure the distance to different stars. And by measuring the distance, and by counting the stars in the galaxy, and also by the images by Hubble, they were actually able to estimate the mass of the Milky Way to be 1.5 trillion approximately. 1.5 trillion times the solar mass, or the mass of the sun. Okay. So that is, Gaia is also another space mission, a space telescope actually. Now Hubble probes the early universe. So once it sees a distant thing, that means we are actually seeing the past. So I hope you know all this. So in 1990, the ground-based observatories were only being able to image this far only. Okay, so it is called a redshift 1, or just after only after 6 billion years after the Big Bang. Okay, so this deep we were able to go, but with Hubble deep field imaging, we were able to see the universe after 1.5 billion years after its Big Bang. And 2004 Hubble Ultra Deep Field, we were able to see up to 800 million years just after. Now see, from billion we went to millions actually. In 2010, 480 million, and with JWST we are supposed to see up to 200 million years. Okay, so that is why we are building bigger telescope. That is another purpose. Okay, so we can see how the universe looks at that time. Okay, just after Big Bang. And now the successor of Hubble, anyway, that is called the James Webb Space Telescope, or JWST. Uh, just a second. Okay, so higher that is basically an infrared telescope. Okay, that is an IR telescope. It completely observes in infrared. Okay, so and you can see this is a segmented mirror, not a single mirror. You can see that honeycomb design. This is a segmented mirror, and it consists of 18 hexagonal mirror segment uh, made of gold plated beryllium. Okay, so it is gold plated and beryllium. So gold has the ability to reflect infrared much more than uh, other metals. Okay, and it has the ability to stay without even getting what is called uh, decayed. Okay, and you know that this usually other telescopes are placed something inside a tube, but it is actually open. Okay, so it can actually without even nothing happening in that high radiation. To withstand in that high radiation and all, it's better to have gold, and that is why they chose those materials. So like that. Okay, so now it will get reflected, and here we have the secondary, and it will be reflected back so that they can actually have the instruments there. And all these layers you can see, so a lot of interesting engineering are behind this. You can go and read about them. Okay, so anyway, these are different layers actually. So these layers are actually protecting it from the sunlight that is coming from one side. So why sunlight is a problem? Because the when the sunlight hits one side, it is high. This is a very high temperature at this side, and at this side it is something around some minus temperature. Okay, minus to some minus 200 kelvins actually. So minus 200 degrees Celsius around actually. So that much temperature fall off happening between these layers. So that engineering are, so you should read about them. And why it should be cooled? Because any object that is hot enough at a higher temperature will radiate infrared. So to avoid that, we are placing that telescope in such a way that this part, okay, the back side, this side will be always facing towards sun, and the other side will be always towards objects what we want to observe. And this telescope is not placed around Earth. Okay, it is placed around a specific orbit that is called the L2 orbit or Lagrangian orbit. So when you consider Sun and Earth as together, there are some equilibrium points called Lagrange points, and one of the Lagrange points, that is the L2, is chosen for uh, JWST, where this telescope is orbiting, not the telescope is not placed at L2, it is actually orbiting around L2. And one interesting thing about it is actually when it is orbiting, usually you need something to provide gravity. So if something is orbiting around, there should be some gravity source. Okay, but here there is nothing in the L2. Okay, but the effective force, the net force acting there will effectively push that satellite to the center. It's not like pushing, there is a virtual gravity will be there. So a virtual force will be there. That is how it is orbiting around, and we will try to discuss more about this when we discuss about satellites actually. And Webb launched in 25 December, and its diameter of the mirror is 6.5 meter, and it is almost 2 to 3 times larger than that of the Hubble actually. Okay, so these are the images from Hubble. You can see this, the left one is from Hubble and the right one is from the JWST. So now you can see here most of the part. See here, this is something like, here there is nothing, we cannot see past this. But infrared has a speciality that actually it can more penetrate through uh, dust and all. So here these are all some kind of cosmic dust, okay? So nebula and all, but here this become transparent. See, so that is one advantage why the JWST can even see deeper when deeper than that of the uh, what is called the Hubble. Okay, so that is the advantage. Okay, now this is another kind of a telescope which is dedicated for exoplanet disk detection. So exoplanets are actually the planets that are revolving around other stars, okay, other than sun. Uh, okay. So this is called the Kepler Space Telescope, which is actually detecting transiting planets, or something like when a star is there and a planet is around. The problem with this is actually when you compare with the brightness of the planet, brightness of the star, the planets are so faint. So it is something like a firefly sitting near a floodlight. You cannot even notice it. Okay. So then what method we can employ to detect the uh, planet? So the method is that we cannot even see the stars like a sphere or anything like this. This is just for the demonstration purpose. Now imagine that a star is there. Okay, now the light is coming from the entire disk and we can actually record it. Okay, so when I am recording it, I am getting the full light from that. And now just imagine that a Jupiter like planet is actually crossing through that. Okay, when it comes here, it is actually blocking part of the light that is coming. So that means the brightness will decrease and it keep on moving until here it will be something like this, and it will go some. Okay, so this is what will happen here. So this dip is happening because the planet is blocking some of the light, and it will again repeat. Okay, why it repeats? Yeah, because it is orbiting around it. It periodically it will change. Okay, and telescope is named after Johannes Kepler. Anyway, this telescope is not seeing the star like this. It is only analyzing the light that is coming. So the brightness will be recorded with respect to time. Okay, so as time goes, what is the change in brightness? That is what is being recorded there, and between the using the pattern, they can actually get the period and also how deep it is actually determine the size of the planet. Actually, if it is a big planet, imagine that it is a huge planet, then it will make a large dip. Okay, so based on all this, actually we can calculate maybe sometimes number of planets and the orbital period of planet, and those things can be, and the size of the planets can be determined using this kind of method. So this is called the Kepler Space Telescope. And yeah, now this is an example of image of the same object being captured using different objects or different wavelength. Okay, here this is the famous Crab Nebula. You might have been seen this picture anyway. So this is a Crab Nebula, how it looks in visible light. And now the same when it is in radio, it looks like this. Okay, see here many glows are there. Even these faint regions can made visible using this. And this is how it looks in infrared. Infrared, most of the dust becomes transparent, and this is how it looks ultraviolet. When it comes to ultraviolet, X-ray and gamma ray, you can see that these are all high energy regions. So you can see even at the center you can see something glowing, but it is not visible in all the radio, infrared or visible. You can see something is there. Okay, so there is some high energy is coming from there, and when you look through the X-ray, you can see that even more visible is there. Okay, some jets are actually coming. So actually, this is a supernova remnant. That means there will be at the center there will be a neutron star or maybe a black hole. It's a uh, it can be a neutron star or a black hole which is actually emitting high energy. So that is you can see here. And in gamma ray, it is actually looks like you cannot see any other things here. Okay, you can actually see the gamma rays. So that is why. Okay, here. So that is, and it is not just about the image actually, the beauty of the image, but also each of this image, or when you observe the same object in different type of light, it is actually giving different informations, and that is why we have all the types of telescope here. Now, gravitational wave observatories. So, what do you mean by gravitational wave? So, gravitational waves are actually some kind of ripples in the fabric of space-time. So, according to Einstein, the gravity is not a force, but it is actually a curvature in space-time. Okay, that is a curvature, something like this. If Earth is there, that Earth will make a curvature in space-time. And one more thing, when you see images like this is the only way we can picturize the space-time. Actually, this fabric of cosmos or the space-time is actually all around it. It is not here, everywhere it is. It's actually a three-dimensional thing, but we cannot picturize that. That is why we are using some kind of images like a flat thing. Okay, and now you can see there is a dip. If the object is more massive, it will make a more dip. Even I am also, you are also making a dip in space-time, but it is so tiny. Okay, now imagine that when that dip is there, when that object is orbiting or acceleratedly moving, it will make ripples in the space-time. Just wave your hand is actually making ripples in the space-time. But it is so tiny. Even when the Earth is orbiting around the sun, it is also making ripples. But they are all so feeble. Okay, even the uh, ripples made by two black holes or something like two neutron star or two black hole, when they are orbiting each other, the ripples are strong. Okay, but even though that strong enough uh, gravitational wave are so difficult to detect. That is why this kind of gravitational wave actually predicted by Einstein in 1915. Okay, and we only detected after 100 years in 2015. So just imagine how long we should have to wait for that actually. It is not because of because of there is no gravitational waves are there. It is because the technology for detecting so that tiny thing or tiny waves wasn't there for us. Okay, so now we have, so that then only we are only able to detect the strong gravitational wave because of the orbiting of black holes or neutron stars. Okay, so now what is the method they employ? So the method they employ is something interesting. So consider this as there is some interesting phenomenon of light called the interference. So imagine that two light waves are there. The light wave has an ability to add themselves. Okay, so this is a wave. Okay, okay, just leave it. This is a wave, and there is another wave. Okay, both are in phase, and that means when both comes, both rise at the same time, both dips at the same time. See this here, this bottom or the trough, and both trough matches. So when these two lights are added, they will be constructively interfered. That means it will be something like it peaks become much more even larger than this. They will be added. Now imagine this is the case. What is the reason? Here when one is becoming lower, the other is higher. So they will cancel out. Here this is at say this is a crust and this is a trough, cancel each other. So you get nothing. So the light gets cancelled each other. Okay, so this is something called the interference. Now what they do is that they send a laser light and there is a beam splitter. So what does this beam splitter does? So the beam splitter split this light. A part of this light will be reflected in this direction and part to this direction. Okay, so when it comes back, see, it goes there and it comes back, and it goes there and come back. Okay, and when it comes back here, it will be sent to a point here. Okay, so at this point, this distance is adjusted so that they both comes in opposite. Okay, something like this. Okay, they are out of phase or they are in destructive interference. So normally what will happen, they are arranged the distance between the mirrors and all, so that these two light waves construct destructively interfere destructively interfere sorry, so that there is no light at all. Okay, now what happened, now if something happened to this mirror, something like if the distance of either of this mirror changes, then this condition is lost, so there will be some light. So when there is nothing happen, it is stable. That means there will be no light. Okay, it's darkness, or there is the minimal light. Now, if I change something this distance, then there will be a small light will be detected. So that change in length can only happen either I make it purposefully change, otherwise there should be something. So that something is actually when a gravitational wave comes, that gravitational waves actually changing the space and time. So that space time change is actually changes the distance here. Okay, so that there will be a change in this. So it is something like it is actually stretching this. Okay, it is not that big stretch or anything, it's so tiny. Even the even some even smaller than the size of a proton actually. So that changes. So tiny change will happen. That tiny change will uh, destruct this condition, so that there will be some light, and by detecting that light we are able to detect the gravitational wave uh, there. Okay, so that is how the gravitational wave observatories are basically workings. And LIGO is the first one to create and detect what is a first gravitational wave detection. LIGO is actually comprising of two sites. One is in Livingston and other is in Hanford, two of them. You can see that long pipe here. See, one is going here, one is going in this direction, and one is that direction. They are 4 kilometers long actually. So that is how it is happening. So now advanced LIGO is there. That is another one. And Virgo interferometer is a large, same kind of a design. You can here also you can see. Okay, started making observation again in 2017. Okay, you can see that. So that is about the Virgo interferometer, and this is about the gravitational wave observatories. So gravitational waves are not the usual light. Okay, so the usual light is only that we discussed, gamma ray, X-ray, those things. They are called electromagnetic waves or light. And another entirely different thing is actually this thing called the uh, gravitational wave. Now there is one more thing that is coming from space, that is basically uh, neutrinos, and there are cosmic rays as well. So cosmic ray, uh, neutrinos, then gravitational wave, and the entire electromagnetic waves, all types of light, all together actually now contributes towards astronomy. Okay, and we call it together as multi-messenger astronomy. Okay, not multi-wavelength. Multi-wavelength is for only the electromagnetic spectrum, and if you consider all this together, that is in some cases actually all the scientists from, or maybe there will be large collaboration of all these things, and that is called the multi-messenger astronomy.